This course will identify and describe the different types of direct current, or DC circuits, to include the characteristics associated with each circuit type and how the different types of DC circuits respond when a fault occurs in the circuit. It will also describe how a voltage divider and a current division is accomplished in a DC circuit. These are the objectives for this course. There are several types of electrical circuits. Each type of circuit has distinct characteristics of how voltage and current behave within the circuit. Faults within a direct current or DC circuit will cause various effects depending upon the nature of the fault. An understanding of the effects of these faults is necessary to fully understand DC circuit operation. Every electrical circuit has at least 4 basic parts. 1. A source of electromotive force, or EMF. 2. Conductors. 3. A load or loads. And 4. Some means of control and, in most cases, protection. In an electrical circuit, the electrical current will always flow through the easiest path or the path of least resistance. Electrical circuit diagrams use standard symbols to represent the wires, batteries, switches, and other parts, as shown in the diagram. In the diagram, the source of EMF is a battery. The conductors are wires which connect the various component parts. The resistor is the load, and a switch is used as the circuit control device. With the switch closed, as shown, this electrical circuit is an example of a closed circuit. A closed circuit has an uninterrupted or unbroken path for current to flow from the source, or EMF, through the load and back to the source. There are 2 types of DC circuits, a series circuit and a parallel circuit. First, let's discuss the characteristics of a series DC circuit. There are 2 types of series DC circuits, a simple series circuit and a complex series circuit. Current flow will continue in a series DC circuit until an opening or break in the circuit occurs. An open circuit, or incomplete circuit, exists when an opening or break in the circuit prevents a complete path for current flow through the circuit. As shown in the diagram, an open electrical circuit can be caused by a number of different reasons. Placing a switch in the off or open position, a blown fuse, i.e. the metal conductor in the fuse melts which breaks the current flow path, or when a component such as a resistor or other circuit part is broken or burned out. As we have just seen, electrical circuits can be opened deliberately, such as by the use of a switch, or the circuit may be opened by a defect, such as a broken wire or a burned-out component. When a series circuit is open, there is no current flow in the circuit, and there are no voltage drops across the loads. The entire voltage drop occurs where the opening in the circuit is located. Since there is no current flow to the loads, no power is consumed by the loads, and the total power consumed by the circuit is 0. In a series DC circuit, current flow is only limited by the circuit resistance. If there is no resistance in a circuit, or if the resistance suddenly approaches 0, a very large, possibly dangerous circuit current will flow. A short circuit is a condition that offers very little or no resistance to current flow. Short circuits are usually caused by an inadvertent connection between 2 points in a circuit. Using the diagram as an example, current flow will take the path of least resistance through the shorting connection, and the current flow through resistor R will be 0. The resulting high current flow will probably cause the fuse in the circuit to blow. A short circuit exists if the circuit resistance is so low that circuit current increases to a point where damage can occur to circuit components. When circuit current flow increases due to a short circuit, the energy source terminal voltage decreases due to the internal resistance of the energy source, causing an increased voltage drop within the energy source. The increased current flow resulting from a short circuit can damage circuit components and power sources. It can also burn insulation and start fires. Protective devices such as fuses or circuit breakers are provided in circuits to protect against short circuits. In a DC series circuit, the total resistance of the circuit is equal to the sum of all the resistance parts of that circuit. This is represented mathematically by the equation on this slide, where RT equals the total circuit resistance, and R1, R2, and R3 equals each individual resistance value. Now, let's go through an example using the series resistance equation to determine the total circuit resistance of a DC series circuit. For this example, a DC series circuit contains a 60 ohm, a 100 ohm, and a 150 ohm resistor. What is the total circuit resistance? Using the series resistance equation, insert the resistance values for R1, R2, and R3 with their applicable units of measurement into the equation. Add the resistance values together to determine the total circuit resistance, being sure to include ohms as the unit of measurement. Similar to the total resistance in a DC series circuit, the total voltage across a series circuit is equal to the sum of the voltage drops across each resistor in the circuit. This is represented mathematically by the equation on this slide, where ET equals the total voltage, and E1, E2, and E3 equal the voltage drops across the associated resistors. Ohm's law may now be applied to the entire series circuit or to individual component parts of the circuit. To find the total voltage across a series circuit, multiply the circuit current by the total resistance. When used on individual component parts, the voltage across that part is equal to the circuit current times the resistance of that part. Substituting the individual component voltage equations into the series circuit voltage equation yields the equation shown on the slide, where the total circuit voltage equals the sum of the individual component voltage drops as expressed using the individual component voltage equations. Let's go through an example where you need to determine the voltage across each resistor in a DC series circuit. A 120-volt battery is connected in series with three resistors, 40 ohm, 60 ohm, and 100 ohm. Find the voltage across each resistor. In this example, you are given the total voltage and the resistance values for each resistor. To find the voltage across each resistor, you will need to determine the circuit current using Ohm's law. Remember from the units of measurement module that the circuit current is equal to the circuit voltage divided by the circuit resistance, or, for this example, the total voltage, or ET, divided by the total resistance, RT. Since the total voltage is known, substitute that in for ET in the equation. Now, calculate the total resistance by adding the three resistance values, and then substitute the total in the Ohm's law equation for RT. Then solve the equation. For this example, the circuit current is 0.6 amperes. Now that we know the circuit current is 0.6 amperes, we can find the voltage across each resistor in the circuit using Ohm's law. Remember from the units of measurement module that voltage is equal to the circuit current times the resistance, or, for this example, the voltage across each resistor is equal to the circuit current times the individual resistance value. Substitute the circuit current for I and the individual resistance values in each equation, then calculate the voltage across each resistor. For this example, the voltage across resistor 1 is 24 volts, resistor 2 is 36 volts, and resistor 3 is 60 volts. The voltage across resistors R1, R2, and R3, that is, E1, E2, and E3 respectively, are known as voltage drops or IR drops. Their effect is to reduce the available voltage to be applied across the other circuit components. The sum of the voltage drops in any series circuit is always equal to the applied voltage. This can be proved using the series circuit voltage equation by substituting in the known values for total voltage and the individual resistor voltage drops, then solving the equation. Voltage sources such as the batteries, or cells, can also be connected in series. The negative terminal of one cell is connected to the positive terminal of another cell. Each cell adds its individual cell voltage to the previous cell. For example, if each cell is 1.5 volts, then the voltage measured across one cell is 1.5 volts. Across two cells is 3 volts. Across 3 cells is 4.5 volts. Across 4 cells is 6 volts, etc. Although the voltage increases as more cells are connected in series, the current is the same through all the cells. This is how batteries are made with higher voltages. The small rectangular 9-volt batteries used in electronic toys and equipment are made up of 6 1.5-volt cells connected in series. The 6 cells are surrounded by a metal case for strength, with the battery positive and negative terminals attached to one end. Now that you understand the characteristics of a series DC circuit, let's discuss the characteristics of a parallel DC circuit. Simple parallel circuits are circuits with two or more components connected across the same voltage source, or, stated another way, a circuit which has more than one path or branch for current to flow through the circuit. In a parallel circuit, the voltage drop across each branch of the circuit is the same as the source voltage, meaning each parallel branch has the same voltage. Current flow, however, is dependent on the load in each branch. When the current leaves the voltage source, a portion of the total current will flow through the first branch, that is I1. Another portion of the total current will flow through the second branch, that is I2, and the remainder of the total current will flow through the third branch, that is I3. Since the voltage drop across each branch of the circuit is the same, current flow through each circuit branch will be different based on the load resistance in that branch, as shown using Ohm's law. Since a parallel circuit has more than one path for current to flow, an open circuit will affect the operation of a parallel circuit differently depending on the location of the open circuit. Parallel circuits are more likely than series circuits to develop damaging short circuits, since each load is connected directly across the power source. When a parallel circuit becomes short-circuited, the effect on the circuit is similar to what occurs in a series circuit. There is a sudden and very large increase in circuit current. If any of the parallel branch loads become shorted, the resistance between the power source terminals is practically zero, which causes a large current increase. If a series load in a parallel circuit becomes shorted, the resistance of the other parallel branch loads keeps the circuit resistance from dropping to near zero, which limits the amount of current increase due to the short circuit. The total current flow in a parallel circuit equals the sum of the currents flowing through each branch of the parallel circuit. Using Ohm's law, the current flow of each parallel branch circuit can be calculated by dividing the applied voltage by the parallel branch circuit resistance. Remember, the voltage drop across each parallel branch is equal to the applied voltage to that branch. For a three-branch parallel circuit, the equations for calculating each parallel branch current flow is as shown. Once the parallel branch current flows are known, the total current flow can be calculated by totaling the three-branch current flows. Now, let's go through some examples determining the current flow through various parts of a parallel circuit. In this first example, a parallel circuit with three branches is connected across a 115-volt source. The three branches of the circuit have current flows of 3 amps, 3 amps, and 2 amps for branches 1, 2, and 3 respectively. What is the total circuit current flow? Since all three parallel branch current flows are known, add the three current flow values to find the total circuit current flow. In this second example, a parallel circuit with two branches is connected across a 120-volt source. The total circuit current flow is 30 amps, with 22 amps of current flow going through parallel branch 1. What is the current flow in parallel branch 2? Since the total circuit current flow and one parallel branch current flow is known, solve for the unknown parallel branch current flow using the current flow equation. In this third example, a parallel circuit with three branches is connected across a 120-volt source. The resistance in branch 1 is 15 ohms, the resistance in branch 2 is 20 ohms, and the resistance in branch 3 is 10 ohms. What is the total circuit current flow for this parallel circuit? Since only the applied circuit voltage and the resistance values for each branch of the parallel circuit are given, first, solve for the unknown parallel branch current flows using Ohm's law. Now that we know the parallel branch current flows, add these current flows to determine the total circuit current flow. Total resistance in a parallel circuit can be found by applying Ohm's law. Applying Ohm's law to the previous example parallel circuit, the total resistance can be determined by dividing the applied voltage by the total circuit current. The total load connected to the circuit's 120-volt source is the same as the single equivalent resistance of 4.62 ohms connected across the source. The term equivalent resistance refers to the total resistance a combination of loads presents to a circuit. Total resistance in a parallel circuit can also be found when only the resistance values of the parallel branch circuits are known using the equation shown on this slide. Solve this total resistance equation by either inverting both sides of the equation or by cross multiplication. Let's apply the parallel resistance equation to the previous example to see if using this equation provides the same equivalent resistance value as using Ohm's law. Given the parallel resistance equation, insert the values for the three parallel resistances into the equation and then determine the lowest common denominator to simplify the equation. Invert both sides of the equation, or cross-multiply, and solve the equation for the total resistance. As you would expect, the calculated equivalent resistance value is the same using both Ohm's law and the parallel resistance equation. Note, whenever resistances are in parallel, the total resistance, or equivalent resistance, is always smaller than any of the single parallel branch resistances. There are two simplified equations you can use when certain circuit conditions exist. The first is if each branch of a parallel circuit contains an equal resistance. In this case, the total resistance of the parallel circuit is equal to the resistance of one resistor divided by the number of resistors. To see how this works, let's go through one example. A circuit contains 5 lamps connected in parallel, each with a resistance of 40 ohms. What is the total resistance of the parallel circuit? Since all 5 lamps have the same resistance, insert 40 ohms for the value of R and insert 5 for the total number of lamps, that is, resistors, in the equation and then solve the equation. In this example, the total resistance of the parallel circuit is 8 ohms. Note, this same total resistance value would be computed if the parallel resistance equation were used. The second simplified equation can be used when a parallel circuit contains only 2 branches. In this case, it may be easier to determine the total resistance by multiplying the 2 branch resistances and then dividing that product by the sum of the 2 branch resistances. It is important to remember that this equation may only be used if there are 2 parallel resistances. It will not work if there are more than 2 parallel resistances in the circuit. Let's go through an example of a 2-branch parallel circuit using this equation. In this example, a 2-branch parallel circuit has a resistance of 12 ohms in one branch and 4 ohms in the other branch. What is the total resistance of the parallel circuit? Using the simplified equation, insert the values for the 2 parallel resistances into the equation as shown, and then perform the mathematics to solve the equation. In certain cases involving 2 resistances in parallel, it is useful to find an unknown resistance to obtain a certain total resistance. To find the appropriate equation, we start with the equation for total resistance and let the known resistor be R and the unknown resistor be Rx. Now, cross-multiply the equation and then transpose the equation. Next, factor the equation and solve the equation for the unknown circuit resistance. Similar to other electrical components, voltage sources can also be connected in parallel. When voltage sources, such as batteries, are connected in parallel, the voltage is not changed, but the long-term current capacity of the voltage source is increased. Each cell contributes its individual current capacity to the circuit. To connect voltage sources in parallel, each cell's positive terminal is connected to the positive terminal of all the other cells, and the negative terminals of the cells are connected as well. This type of connection is made when a car has a dead battery and is jumped by another battery. Also, This is the connection method used when charging a battery with a battery charger. So far, all we have discussed are simple series and parallel circuits. Most electrical circuits, however, contain both series and parallel elements in the circuit. These types of circuits are called complex circuits. Parallel circuits can have two or more components in any branch of the circuit. This type of complex circuit is a parallel circuit with series elements. A parallel circuit may have a component in the circuit that is in series with two or more of the parallel branches. This type of complex circuit is a series circuit with parallel elements. A voltage divider, or network, is used when it is necessary to obtain different values of voltage from a single energy source. The voltage divider works by utilizing the voltage drop across the circuit components to obtain different voltage values. This can be very useful when a piece of equipment, such as a TV or VCR, requires different voltages to power different parts of that equipment. Let's look at an example voltage divider to see how different voltages can be obtained. In this example, a 24-volt voltage source is connected to 3 resistors in series with a total resistance of 24 ohms. Using the Ohm's law equations shown on this slide, calculate the total circuit current flow, then each voltage drop shown in the diagram as they appear. As you can see, a voltage divider can provide a variety of different voltages which can then be used to supply other components. Sometimes it is necessary to find the individual branch currents in a parallel circuit when only resistance and total current are known. When only 2 branches are involved, the current in one branch will be some fraction of the total current. The resistance in each circuit can be used to divide the total current into fractional currents in each branch. This process is known as current division. In a parallel circuit, the current divides, but in a series circuit, the voltage divides or drops across each load that is in series. Simply put, voltage divides in a series circuit, current divides in a parallel circuit. When only 2 parallel branches are involved, use the equation shown on this slide to determine the current flow through each branch of the parallel circuit. Note that the equation for each parallel branch current has the opposite parallel branch resistance in the numerator, since each parallel branch current is inversely proportional to the parallel branch resistance. Let's go through an example using the equations for current division. Find the parallel branch currents for the circuit shown on this slide. Once one parallel branch current is determined, you can use the parallel circuit current equation to find the other parallel branch current. All voltages and currents in a circuit have polarity as well as magnitude. The overall polarity in a DC circuit is from the negative DC terminal through the rest of the circuit to the positive DC terminal. In a series circuit, the current is the same at every point in the circuit. However, electrons gain energy in a voltage source, which is measured as a voltage rise. Conversely, electrons lose energy in a load, which is measured as a voltage drop. Since a source is a voltage rise and a load is a voltage drop, the polarities will be opposite. The easiest way to find these polarities is to use the direction of the electron current as a basis. Where the electron current enters the load, the voltage is negative. This holds true regardless of the number or type of loads in the circuit. The voltage drop across a load is opposite to that of the source. Each load voltage drop opposes the source voltage and reduces the available voltage for the other loads. This is because each load uses energy, thereby leaving less energy for other loads. Symbols representing electrical components are needed for reading and sketching electrical circuits. The diagram on this slide illustrates some of the electrical schematic symbols and the name of the component each symbol represents. Some of these electrical components and symbols have already been described previously. The remaining electrical components and symbols will be needed in subsequent e-learning modules.